Combination sum 4. Given an array of distinct integers nums and a target integer target, return the number of possible combinations that add up to target. The test cases are generated so they can fit in a 32-bit integer, so we don't have to worry about doing longs or longs. And so we're given a test case here, so we have 1, 2, and 3, and the target is 4. So the possible combinations you can do to reach 4 is take 1 4 times, take 1 2 times, and then 2, take 1, then 2, then 1, 1 and 3, 2 1 1, 2 2, and 3 1. So if you can see here, we can, one of the things we can note is they're permutations, not combinations. So if you can see here, 2 1 1 and 1 2 1, they're the same. Like 1 1 2 and 1 2 1 and 2 1 1, they're the same. They contain the same amount of the same coins, but they're in different order, so they count as different things. So let's start writing our assumptions. So restate the problem. So we're gonna have an array of possible options we can pick from, and we're gonna have a target number that we're trying to reach using those specific numbers. So this is very similar to another problem called coin change, and maybe it's better to frame it this way. So in this case, our array, let's say, represents amounts of coins. So you have a coin that is cost 1, a coin that is cost 2, and a coin that is cost 3. So you're trying to pick a selection of coins that add up to 4. So for example, here you can pick 4 coins of value 1. You could pick 2 coins of value 1 and 1 coin of value 2. And you could do this in like different ways. So in this case, the order in which you pick the coins matters. That's why I mentioned at the beginning, permutation, not combination. So picking 1, 1, and then 2 is different from picking 1, then 2, then 1, even though you're picking the same coins and the same amounts. So we've restated the problem. Now we have edge cases. So our edge cases, there's one right here, which is neither of our coins are able to, no combination of our coins can add up to the value that we need. So that's one possible issue there. Maybe we have no coins, but that's not a problem we have to worry about, because we see here that our coins or our nums have to be of length at least 1. So we're gonna have at least 1 coin. So we don't have to worry about that. It also says that the coins are all gonna be positive, so we don't have to worry about negative coins. In fact, I think that's the follow-up question here. We're gonna talk a little bit about that after we've solved the problem. And then the target is also positive. So for this is a dynamic programming problem. And so the way you can tell is normally dynamic programming, it asks you to optimize. So it asks you what's the least amount, like what's the way I can solve a problem using the least amount of resources or gaining the most amount of possible value. Or like in this case, they ask you for the total amount of combinations you can do something. Those are the typical problems, like optimization problems. And normally you can solve them either through dynamic programming, or maybe there's a greedy way of solving it. You should try to figure out if there's a greedy way first, but there's no, like from my experience, I can see that there's no greedy way of solving this. So one thing that I'm gonna ask you for you to notice here is the target can go from 1 to 1,000. So this is a very low amount of possible values. So one of the things you can think of by looking at the constraint is, can I iterate over all the possible numbers up to the target to find out the solution? And that's going to be something very achievable. So how are we going to do that? So in this case, we have these 3 options for the coins. So let's say our target in this case is 4. So I'm going to make an array up to 4. And how can we break this problem into sub-problems? So that's a lot of like what dynamic programming is asking. So if you think about it, we're trying to pick coins that add up to the target 4, but a sub-problem could be take coins that add up to 3 or that add up to 2, and then you can build the solution to 4 using those sub-problem solutions. I'm gonna create an array that goes from 0 to the target, and that's gonna count the amount of ways I can get to that amount. So how many ways can I get to 0? 1, by having nothing, by adding no coins. We're gonna check our possibilities from here. So starting at 0, we have 1 way. Then if we have 1 way here, then we can reach other points using the coins that we have. So for example, if we have 0 and we just take the coin 1, then we have one way of getting here to 1 by picking the coin 1. Then if we pick only the coin 2, then we have one way of getting the coin 2, which is just picking that second coin. And if we want to get to 3, we have one way so far, which is from 0, pick the coin 3. So we're only checking from 0 for now. I know you can get to 3 in other ways, but we're going to build that answer as we go along. And then this is going to be 0 for now. So we're building that answer. So we've iterated all the possibilities of coins, of amounts we can reach from 0 by taking one coin. Now we can move on to the next one. So if we're at amount 1, we can pick any of these 3 coins to reach other amounts. So from 1, we could reach 2 by picking another coin. So we're going to add the amount of ways we can reach to 1 to 2, if that makes sense. So in this case, we can only reach 1 by picking the coin 1, but we can reach 2 by picking the coin 2, or by doing 1 and 1. Yeah, so this is going to be 2 now. So this is going to be, we're going to add 1 to that result. We're going to add this to here. So that's going to be 2. We're going to do the same for 3. So for 3, you can reach it by picking 3 or by picking 1 and then 2, right? So let's add the amount of ways we can reach 1 to 3. So that's going to become 2 as well. And how can we reach 4? So far we haven't been able to reach 4, but we can reach it by picking 1 and then 3. So we can update this value right here to be now 1. So we've iterated over all the possible ways we can reach other values picking these coins from the amount 1. So now we go to 2. So from 2, we can pick any of these 3 coins. So if we pick 1, we can go to 3. And so we're going to add the amount of ways we have here to the amount of ways that are in 3. Because now you're going to be able to reach 3 by having 3, by picking the coin 3, by picking coin 1 and then 2, by picking coin 1, then 1, then 1 again, or by picking coin 2 and then 1. As you can see, this is different from this. So we count them both. So there's 4 ways so far we can make it. So if you can see, we add the amount of ways that we've been able to reach 2 to the amount of ways we can reach 3, since we can reach 3 from 2. So this is going to be 2 plus 2. It's going to become 4 ways. Now next coin would be 2. So 2 plus 2 is 4. So now, so far we have only been able to reach 4 by doing 1 and 3. Now we can reach it in different ways. We can pick 1, 1, and then 2. Or we can pick 2 and then 2. So we're going to add 2 amount of ways to 4. So it had 1 plus 2. It's going to become 3. So far we're able to reach 4 in 3 ways. 1 and 3, 2 and 2, and 1, 1 and 2. Yeah, so we've checked all the coins, I believe. Yeah, we've checked 1, 2. Actually, we haven't checked 3. So 2 plus 3 is 5. Do we need to calculate 5? No, because that's above our target and we don't have negative numbers to come back. So we don't need to calculate 5 actually, so we can skip this step. Next, so we did 2. Now we're going to go with 3. So we've been able to reach 3 in 4 ways. 1, 1, 1, 2 and 1, 3, and 1 and 2. Now let's try adding 1, 2, 3. So which gives us 4. So now these ways all are all added to here, to the 4. So if we can work with this answer, for example. So these are all going to be added to the answer for 4. And you can see that here. So for example, we had 1, 1, 1 for 3. If we add 1 to that answer, it becomes 4. So we have 1, 1, 1, 1 to reach 4. 2, 1 to reach 3. Well, now we have 2, 1, 1, 1, 2, 1, 1 to reach 4. We had 3 to reach 3. Now we have 3, 1 to reach 4. And we had 1, 2 to reach 3. Now we have 1, 2, 1 to reach 4. So we have now 4 more ways that we can get to 4. So we're going to add the amount of ways that we can reach to 3 to reach to 4. So it's going to become 7. We can add then like 2 to 3 and 3 to 3, but that goes like after our target, so we don't need to actually calculate those. And from 4, we don't, like I said, if we add 1, it's going to be outside our target. We've already reached our target, so we don't need to calculate it anymore. We've already calculated all possibilities. The answer would be 7 for this case. I'm going to go double check. You can see here, the answer is 7. So how do we program this? So here we're going to create an array for the answer. I'm just going to call it ans for answer, and that's going to be up to target, and we're going to fill it with zeros. Now, we're going to iterate over every possible value up to the target. So I less than target, I plus plus. And so as we did in the beginning, if you see here, we initialize the answer for 0 with 1. So there's one way we can reach 0, and that's by having no coins, right? So we're going to do that. Ans 0 is going to be equal to 1. And there's a thing I actually didn't cover here, and it's if you ever reach an amount that you're not able to get to with any of the coins, then you don't need to calculate that amount. So if we had, for example, 2 and 3, let's say we didn't have the like a coin of value 1, we just had coins of values 2 and 3, then right here, this number, we wouldn't be able to reach 1 because we don't have a coin that is of value 1, so we wouldn't be able to reach the amount 1. We can't break the 2 coin in half, or the 3 coin in 3 parts, and call it that's of value 1. So what we're gonna do in that case, if we reach here and we see that we have no way of getting that amount, then we don't need to calculate any other amounts we could get by adding coins, because we can't get to this amount, so we can just skip it. So if my answer for like this specific amount is not 0, then what? So then we're gonna add the amount of ways that we can reach to the current value to the values plus the coins. So we're gonna iterate over the nums, or the coins, in the way I'm explaining it. So for int coin, we're just gonna call it coins. It's just gonna be easier. So if the current amount plus the coin is above my target, I don't need to calculate it. So if I plus coin is bigger than target, we're gonna continue. Otherwise, actually it might be better to just do, instead of that, we only do if it's less than or equal to a target, then we're doing our calculations. We're gonna say ans of I plus coin. We're gonna add the amount of ways you can reach the current number to that. Plus equal ans I. Right? We're only gonna do that if it's less than the target. So we're gonna calculate our intermediate answers and use it to find the final answer. And at the end, we're gonna return the answer for the target. Actually, this should be target plus 1. We're gonna record the answer for the target. And let's run it with the test first. Okay, so it passed. I'm pretty sure this should pass for the actual answer, but it's maybe not. Maybe I'm an idiot. The problem was that like some intermediate answers that like didn't lead up to the right answer don't fit in a 32-bit integer. So in that case, I mean, I feel like the problem is just designed weirdly in that case, but in that case what we can do is just ignore any answers that overflow, because those answers probably don't lead us to the right answer. I mean, I didn't ignore them in this case, I just modded it so it wouldn't overflow. You could probably just like skip it and like stop calculating that. But yeah, in this case I just made sure it didn't overflow, and we would reach the answer anyway because we know for sure that it's not going to overflow according to the problem. There's a follow-up here. What if negative numbers are allowed in the given array? How does it change the problem? What limitation do we need to add to the question to allow negative numbers? So right now we're only, like the example I gave, we're only dealing with like positive numbers. And so I'll show you the problem that you encounter if you start dealing with negative numbers. Delete. Right. So let's say you have a coin 1, a coin that's 2, and a coin that's -1. So we have a coin that's value 1, a coin that's value 2, and now we've added a negative number here. So what's the problem? We're asked to calculate the total amount of ways we can reach up to target. Let's say that target is 4 again. So one of the problems you're gonna get to here is you're gonna have like a cycle if you start drawing the graph. So if we draw the graph, this is 0. From 0 you can go to 1, you can go to 2, and let's ignore -1 for now. Then from 1, if you use the -1 coin, you go back to 0, and then you go back to 1, and then you go back to 0. So you have like a cycle here. Actually, if I draw the edge like back into 0, then you have a cycle where you can go back and forth. So that means your total amount of ways that you're going to be able to reach the target amount is going to be infinite, right? Because you're going to be able to do this in an infinite amount of permutations. So for example, if you're trying to reach 4, you could do 1 -1 2 2, or you could do 1 -1 1 -1 2 2, or you could do 1 -1 1 -1 1 -1 2 2. Like you can see, and you could do this infinitely. So you're gonna have an infinite amount of permutations to be able to reach a target number. So that's a problem, because we're trying to count the amount of ways, but if they're infinite, we can't count them, right? So what do we need to change about the problem? What limitation do we need to add to allow negative numbers so that we can still calculate the answer, but we can use negative numbers and we don't have this infinite problem? So what you would do in that case is limit the amount of times you can use a specific coin. Right now we can use a coin an infinite amount of times. So if we want to use this -1 10,000 times, we can to reach the answer. But that generates this infinite amount of ways to reach the number problem. So if we limit the amount of times we can use a specific coin to, let's say, 1, then we don't have that problem anymore, because we can't do this thing. Right? If we say like we can only use each coin once, we're gonna be going like 1 -1, and then we can't use the 1 or the -1 again, so we're gonna have to use the 2, and we can see we can't reach 4 because the maximum we can reach is 3. 1 2 1 plus 2. So if we limit the amount of coins to 1 each, or like to a finite amount of coins of amount you can use each coin, then we don't have that loop, because you can't go back and forth infinitely, because you don't have an infinite amount of coins, right? So that's regarding the follow-up.